Hello, this is Jonathan Templin, and this is a lecture about path analysis. Exciting topic. Let's get into it. So this lecture assumes that you have some knowledge of Lavon, the Lavon software, or the structural equation modeling framework. I provided that knowledge in the previous lecture on multivariate linear models, so that builds upon that. And now what we're going to do is dive into how we adapt those multivariate linear models, where each outcome was only was being predicted by a set of predictors, and allow other outcomes to predict other outcomes in the model itself. So that's what a path model is. So we're going to talk about how we statistically identify path models and provide a few basic tips on the identification of what to try to make that a little bit easier to see if a model will provide statistical estimates. And then we're going to get into some of the details, how we modify models to ensure model fit happens, and then how we quantify what we call direct and indirect effects. So direct effects you're familiar with already. Those are regression slopes. Indirect effects are built on the model itself, talking about how variables combine to produce an effect on an outcome. This was what will get us into the topic of mediation. And finally, we'll talk about the different other issues that show up in path analysis, apart from the introductory lecture that this is. So let's move forward. Again, the data are based on a paper I found that does a nice path analysis. This paper was from 1994 in the Journal of Educational Psychology. There was a sample of 350 undergraduates, of which 229 were women, and about 10% of the observations were missing. 10% of the observations across the data set itself into the variables here. I simulated these data based on the characteristics of what I found in the paper. I used a multivariate normal distribution for that, for most of the continuous variables, actually for all the continuous variables. And you'll note that the results won't match exactly what the paper has. And that's part of the reason, part of the issue is coming from the simulation. Part of it is the range of variables. So some of the variables in this study had sort of truncated ranges, so floors and ceilings on psychological assessments or tests. And so that's what ends up happening. So if you see these results and you look at the paper and you say, oh, they're not the same. Yeah, that's part of the business is simulated data. So now here are the list of variables. We have gender, we have math self-efficacy with a reported reliability of 0.91. This is a scale. So anytime you see this reported reliability here, know that's a scale. Also note that this is violating a basic assumption of a linear model or a path model. That assumption is that each variable is measured perfectly. Psychometric instruments and the scores that they produce are not perfectly measured. That's why we use indices of reliability to talk about how much error is in each of those measurements, or how much actually lack of error. 1 minus reliability is really the error. So math self-efficacy is a variable that assesses the math confidence of college students. We have perceived usefulness of mathematics, talking about whether a student finds mathematics useful. And then we have math anxiety, whether math makes a person anxious. We have math self-concept, which I'm not really familiar with, but sure, why not? I have a self-concept of myself as a mathematician, I think. I haven't really thought that way. And then we have prior experience at the high school level. Now, this is the number of years of high school during which students took math courses. And we have prior experience at the college level. Now, that's the number of courses taken at the college level itself. It's credit hours. And then we have mathematics performance. The reported reliability is 0.788. Basically, it's the total of correct responses out of an 18-item multiple choice test in mathematics. This was the path model that was in the paper itself. So again, we have gender that predicts high school math experience and math self-efficacy. We have high school math experience, which is said to predict college math experience, math self-efficacy, math self-concept, and mathematics performance. We have college math experience, which directly predicts math self-efficacy and math self-concept. And then these variables in the middle, math self-concept predicts mathematics performance, and math self-efficacy predicts perceived usefulness. Both perceived usefulness and mathematics performance. So interestingly, is stumbling over my words because I'm trying to think about what to say next. What you can say is in this model, what we're thinking about is if it's possible to test whether math self-efficacy mediates the relationship between math experience and math performance or perceived usefulness. Similar to that, math self-concept is said to mediate the relationship between high school math or college math experience and math performance. So that is our path model. The red arrows refer to what we call a direct effect, that is a regression slope, basically. And the dashed arrow represents a residual variance. So each of the boxes that you see a dashed arrow on, these are what we call endogenous variables, variables whose variance is being explained by the model. And then we have gender here, which doesn't have a dashed arrow. That's an exogenous variable. Now, gender, in our case, we're going to use a binary variable to index gender. That binary variable, we know that people vary. We know that the sample had, what was it, roughly, about 2/3 of the sample were close to 2/3 were women. So this varies naturally, but we're not describing why it varies. In fact, that doesn't seem to make a lot of sense. It's hard to think of biological sex as being a mediator in a path model, because there is a causal process for that. It's how each of us come to be in people. Anyway, let's move on. We're getting into the identification of path models first. Now, identification is not like you look at this picture and you say, hey, that's a path model, I identified it. No, identification refers to the statistical concept that we have to have a certain structure of the model itself to be able to estimate the parameters uniquely. An unidentified model is one where we would have multiple types of parameters that all have the same type of fit, likelihood itself. So model identification is necessary for statistical models to have meaningful results. We can't have too many unknown variables, which are parameters, those unknown values, and not enough places to put the parameters in the model distribution. So think of it this way. In our multivariate normal distribution, which is going to underlie this lecture and this path model that I'm talking about today, I will note as a side, that doesn't mean all path models, but just to get you introduced to path models as a concept, we'll use a multivariate normal distribution. We know that that has a mean vector and a covariance matrix. And from that, we know there's a set of unique parameters that show up in that distribution, the parameters themselves. So if we would have fit just estimated using maximum likelihood, the mean vector and the covariance matrix, we'd have a set number of parameters in that model. That turns out that is the saturated model. Well, it turns out our path model has to have fewer parameters in it. Now, those are the regression coefficients, the residual variances, the intercepts. That number of parameters has to be less than the number of model parameters in the saturated model. And we saw this in the previous lecture where we talked about degrees of freedom being the difference in parameters between a saturated model and the model you're specifying. If that difference is 0, we call that just identified, which is estimable, which is identified. If that difference is positive, so basically the saturated model has more parameters than your model, that would also sometimes be called over-identified, which would be estimable also. The bad case is where you have too many parameters in your model and not enough in the saturated model. That is unidentified. That is a bad thing to have happen. So what I was just describing there is a very basic way of looking at identification. Actually, it has a name. I'll show that on the next slide. But for path models, there is a little bit more that you need to identify the model itself. And that's because in a path model, the predicted variables can also predict other variables at the same time. So we think of identification in two different ways. There's a global identification, that is the count, basically. Is the number of parameters less than or equal to what's in the saturated model. And then we think of local identification, thinking about it so that each pair of equation or each individual equation shown in the path model is identified. And so if you get both of the global identification, the count, and your local identification, sort of the way each pair or set of equations may be, if you get both of these, you have overall identification and you can get good parameter estimates in your model. So global identification, the count, sometimes gets called the T rule. We call it a necessary but not sufficient condition for path models to be estimable. You have to have the count. And that's, again, what I was mentioning before. If you look at your underlying model as being multivariate normal, what we need is the number of parameters in our model to be less than or equal to the number of elements in the mean vector and the unique elements in the covariance matrix. That's the saturated model itself. So if we want to quantify this, if we say that S is the number of all endogenous and exogenous variables, so that's the number of variables in the data total, then the total unique elements that we have are S plus 1 over 2, S times S plus 1 over 2. Now, the classical definition of the t-rule counts the following parts of the model as model parameters. So we get the direct effects, those are regression slopes. We get residual variances. We have residual covariances. We have exogenous variances. And we have exogenous covariances. So this is the variances and covariances of the models that are not, the variables that are not being predicted. We have the residual variances and covariance of those that are. Now, missing from this list are the set of exogenous variable means and the set of intercepts for endogenous variable means. These are the means of the variables outside of the model and the means of the endogenous slopes themselves. These would fall under the mean vector more technically. Everything else falls into the covariance matrix. So if you actually want to take the total count that we're talking about, this t-rule, this top part refers to this set needs to be less than or equal to the covariance matrix parameters in the saturated model, whereas the intercepts themselves or the means has to be less than or equal to the number of elements in the mean vector of the model. So each of the missing entities are part of the Lavon likelihood function. Again, we're going to use the Lavon package to estimate this, but they're considered saturated so that no additional parameters can be added. So what I mean by that is, by default, Lavon will estimate the means of every exogenous variable and the intercept for every endogenous variable. So they don't enter that equation for the covariance matrix, this top part here for the t-rule. And often they're forgotten. So if you read textbooks about path analysis, the mean vector side is often forgotten because it ends up being saturated and it fits perfectly. But that's not always the case. And I just want to leave room in your mind to be thinking about it that way. So here's our previous model, our multivariate linear regression path diagram, where we started or we left off the last time. We took mathematics performance and mathematics usefulness and predicted both of those by high school math experience and college math experience. You'll note that both of these two variables are called endogenous variables. We have a residual variance for each. We have a residual covariance for each. High school math experience, college math experience are called exogenous variables. They would also have a variance and a covariance, right? They vary in what the values are, and they covary together. But we're not explaining what that variance and covariance happens to be. If we want to quantify this, we know we have two endogenous variables, we have two exogenous variables. That means we have, in the saturated model, a total of 10 unique covariance matrix elements. So what I'm talking about here is, think of that, if we were just to take all four of these variables, strip off all the arrows, all the double-sided arrows, all the dashed lines, just look at these four variables, what would the multivariate normal covariance matrix look like? Or what would the covariance matrix look like? It would be size 4 by 4, 4 rows, 4 columns. Down the diagonal, there'd be a variance for each variable, 1, 2, 3, 4. And in the off diagonal, you'd have a covariance between each pair of variables. There would be 6 of those. So that's where this 10 comes from. Now, if you go and count those model parameters that apply to the covariance matrix, that would be each of the parameters that you see on this screen. Now, you'll note on the screen, we don't have intercepts for each of these endogenous variables, and we don't have means for each of these exogenous variables. So, in the count of those parameters, if you look at all the lines, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 10 parameters in our model. There's 10 possible elements in our saturated model covariance matrix. So we'd say that this was just identified. So when the number of covariances is equal to the number of model parameters you want to estimate, we call that just identify. It's necessary for identification, but as we saw before, the degrees of freedom in our saturated model likelihood ratio test became 0. So there's actually no model fit of indices available, which actually means model fit is perfect, which is great. Alternatively, if we have way more covariances in our saturated model than we have model parameters, that is also identified. We call that over-identified, and we will see model fit indices. That'll be the case in this model as we go. Actually, not the one you just saw in our full path model when we get to that part of this lecture. Finally, if the number of covariances in our saturated model is less than the number of model parameters, the model is not identified. We can't get results. It won't estimate. Lavon won't do it. So those are the three statuses of path model identification, but that's the global identification. For most of your research designs, the global identification will work for the most part, but we actually have to go a step further and define a couple different ways of what path models look like. So technically, global identification works if you have a recursive path model. Now, to define that, a recursive path model is one where the direct effects are unidirectional. Right? There's no feedback loops. And that big path model we started our lecture with is an example of a recursive path model. Alternatively, you could have a non-recursive path model, one where there are bidirectional or feedback loops for one or more variables. Now, it's difficult to envision these using cross-sectional data. Oftentimes, when you're in a spot where you might want to draw a non-recursive path model, you will be thinking about sort of processes that take place at different time points. So you might have to think about that, separating a variable by time effectively. Now, there are cases where people have used non-recursive path models. It's much more frequent in econometrics or other parts of social science. And very often you'll see different estimation algorithms used rather than maximum likelihood, just because the process of identifying this is really, you're taking a non-identified model and trying to get parameter estimates the best you can with it. In a joint likelihood setting, that's just impossible. So here's an example of a recursive path model. Let's just take a segment of the model we were working with. If we had high school math experience as our exogenous variable predicting college math experience and predicting math self-efficacy, you'll see that there's a direct effect of high school math on math self-efficacy. There's a direct effect of high school math on college math, and there's a direct effect of college math on math self-efficacy. These variables have a directional arc in that if you started here at my high school math experience and you followed the path, you'd end up at math self-efficacy, either going through college math experience, that would be the mediator, or directly to math self-efficacy. Similarly, with college math experience, you'd end up at math self-efficacy. There's no way to get back to it. Now let's compare that with a non-recursive path model. Right? This model that you see here posits a feedback relationship between college math experience and math self-efficacy. You can think of it this way: the more college math you take, you clearly have to pass those classes to keep moving forward. So if you pass the class, that might improve your math self-efficacy, in which turn now, when the next math class you take, since you feel strongly that you can do math, you can go back and take more college math. That makes sense. It makes sense in a basics, like, I don't know if that makes sense overall, but it seems plausible. Maybe this isn't the grand theory of why people take college math, but it's a plausible idea. But you have to think, okay, in a cross-sectional design, I have a one snapshot part of college math experience predicting or basically having an impact on math self-efficacy. Okay, that feedback loop though might be for the next iteration of college math experience. You might have college math experience at time one, self-efficacy at time one, which may predict college math experience at time two, and so forth. Now that gets into another class of models, longitudinal models, or sometimes in that design, something like a cross-lag panel model. That is not a topic that we're going to talk about with path models here. So just know, for a cross-sectional design, this is a non-recursive path model because you've got a feedback loop. This sort of loop back and forth here, this is not estimable. This sort of breaks the local identification set. So the guiding principles are this: if you have a recursive model with no feedback loops, make sure your number of parameters in your model is less than or equal to the number of unique covariance elements, and that there are no undirected paths connected variables with direct effects. Finally, if you have a recursive model, think about whether you can actually investigate such a model by your data. And if not, you may have to go and think about a longitudinal design. So I think with that, we're now ready to get back to the full path model. This is the set of sort of a flow chart for figuring out how the path model, the process, I guess we call that the workflow these days. Old man Templin here. Let's think of it this way. You formulate your hypothesized model, and you check whether it's identified. If not, I say kick the computer, but really this is kicking yourself. Go back, formulate an identified hypothesized model. Then you estimate the model. Now we're going to use robust maximum likelihoods, so we have to check whether that algorithm converged. If not, if it didn't, that might be some type of issue with your data. Go back and kick the computer again and start over. But if it did converge and estimates are stable, then you got to check for model fit. If there's not good model fit, you have to sort of reformulate the model to get good fit or make some modifications for it. This gets into the danger generalization territory here when you do that. But finally, if you have model fit, sorry, let's go put it this way. You have a model that's identified that you estimated and you got convergence and has good model fit. At that point, we interpret the results. So unlike your linear regression that you saw before, path models have a lot of steps to go through before you go and interpret those results. You have to have an identified model, you have to have an algorithm that converged, and you have to have model fit before you can get there. So we'll go through each of those in our analysis. Now, once again, here's our path model. We have 6 endogenous variables. You can think of that as having 6 regressions all at once. Some of those endogenous variables predict other endogenous variables. So how many total variables? Let's just go and answer our identification question. How many total variables are in our model? There's 7. Gender, high school math experience, college math experience, math self-concept, math self-efficacy, performance and usefulness, math perceived usefulness. How many variables are endogenous? I mentioned that before. There are 6. There's 1 exogenous variable. And is the model recursive or non-recursive? Well, if you take a look at this, start at each variable and trace the path, there's no way to go back to the beginning. So when you trace that path through using direct effects, no way to go back to the beginning. So it is recursive. That is a good sign. We have just achieved identification. Check. Now let's count the number of parameters. There are, in the overall covariance matrix, a total of 28 unique parameters. How many parameters are in a model? Well, we can go look back at the previous slide, but I'll just tabulate them here. 12 direct paths, 6 residual variants, 1 variance of the exogenous variable. So that sums to 19 model parameters for the covariance matrix. 19 is less than 28. We're good. Then you'll note we have 6 endogenous variable intercepts. That's not necessary for the T rule. It's counted, but it is counted in M+. It actually was counted in Lavon as well, too. Lavon and M+ mirror each other quite a bit with multivariate normal path models here. So what this means is we haven't over-identified models, so we actually check that off the list as well, too. We can use Lavon to run our analysis. So if you take the picture from before and you take those 6 endogenous variables, what the path model is doing is saying there's 6 regressions basically happening all at once, right? Here is high school experience being predicted by gender. Here is college experience being predicted by high school experience. And you can go on through each of these equations. That is what we're going to estimate all at once. It's like doing 6 regression models, but simultaneously. Now, how we do this is we get into Lavon and we look at the Lavon code. Remember the Lavon syntax, as we discussed in our previous lecture. In R, syntax is stored in quotes, meaning it's all characters. And we can put commented lines in. So any line that you see with a hashtag or pound symbol, that means that is a comment right there. So those are comments. I structure my syntax so it'd be very explicit. There are faster ways to do it than this, but as you get started, I really advise you to map this onto your mind of what we're trying to estimate. So here are our 6 regression coefficients, our 6 regression lines right here. For instance, on our previous slide, we had sort of reverse order, high school being predicted by gender and so forth. Basically go through your list of regressions, put those in. This is technically the same syntax you'd use in the LM function, or basically what R calls a formula object. We can specify the intercepts. I'm doing that explicitly here. If you don't do this, it's implied, but I'm doing this again to make you sort of tabulate the parameters. Similar to that, we can also specify residual variances. Now that's the double tilde. A double tilde is a variance or covariance. If the variable name shows up on both sides of the double tilde, it's a variance. So each of these we call residual variances because they are endogenous variables. And then if we talk about technically speaking, we could actually add residual covariances between our endogenous variables. If you remember the formulation of the multivariate linear model, the covariance matrix was a residual covariance matrix, meaning these were the diagonals of it, but we could actually have off-diagonal terms there. That is, residual covariances describe how far off we are on two variables more than in a joint sense, like combined. And to begin, we're going to set those equal to zero. They're assumed to be zero in most path models, but we're setting them equal to zero here. And this is where software gets a little bit interesting. You may, if you don't explicitly set them to zero, sometimes in the auspices of trying to be helpful, your software will estimate these for you. I personally find that a little bit distasteful because I want to make sure I know exactly everything that I'm putting in a model before I run it. Other people are like, good, I'll take the help. But I want you to be aware of it, and that's why I'm setting them at zero to begin with. So everything in this first four blocks of my syntax were all for the endogenous variables, the variables being predicted. Now, I'm again being explicit. I don't have to put this in here because Lavon assumes it already, but I'm going to estimate the mean of gender and the variance of gender. Now, I will note, this is where things get a little bit weird because gender is a binary variable, but we're putting it in something that's assuming multivariate normal. We'll talk about that at the end of this lecture. So we put all that into an object. We run the analysis model, and what we end up seeing is it says Lavon ended normally after 68 iterations. That's good. It converged, right? And now, if we just a quick look at the model fit statistics right here, we have to check whether or not the model fit. So let's go through the list. I have a little reminder of what each section of the model fit output looks like. So let's check this first section is the likelihood ratio test between our model and the saturated model. The degrees of freedom are 9. If you remember, that's the difference between the 28 parameters in the covariance matrix of the saturated model and the 19 parameters of our model that go into that. That's the 9. This tells us it has a small p-value. The null hypothesis here is that our model fits as well as the saturated model. This is telling us to reject that saturated that null hypothesis. Basically, this is telling us the model doesn't fit. Now, this is a really sensitive and really powerful test, so oftentimes it's ignored. Although I will say in path analysis, to me, I do want to see this to be a little bit like the burden of evidence is a little bit higher, at least for the models I've run. I guess in big models, it may be a little bit different. Okay, in the next step, this one right here, this is not comparing anything to do with our model. It's comparing the independence model with the saturated model. Now, the independence model is one where the mean vector, Lavon is estimating a model with only the means and the variances, where all covariances are set to 0. Remember, in a multivariate normal, when the covariance is 0, it also implies the correlation is 0. So therefore, this is telling us that the null hypothesis here is that the independence model fits as well as the saturated model. That it doesn't means at least one of those covariances is not equal to 0. Now, again, this is not super useful in the grand scheme of things, but this tells us basically, hey, if all of our parameters of a model are something to do with covariances, which the direct effects are, if this were not significant, we would expect none of those direct effects to be significant either. So that's sort of a big thing. This tells us there's at least some of those direct effects that should be significant. That's what this is telling us. Okay, the next step is what we call approximate fit indices, the CFI and the TLI. I look at the robust part down here. We want both of these to be above 0.95. They're not. So we would say based on this information, the fit is not good. The next section is just the details about the log likelihood and the scaling correction factor for the robust maximum likelihood. This is not so useful in our situation. This is sort of more technical details, but you can, from the difference, you can see where that scaling changes. Finally, the last two bits of model fit, RMSEA is 0.126 from a classical sense or 0.140 in a robust sense. Neither of those are good. We want this RMSEA to be less than 0.05. And if you look at this, the probability that the RMSEA overall is less than 0.05 is 0. So there's no chance that model fits well. And finally, we have the average standardized residual covariance here. It's 0.056. We like to think that good fit's less than 0.05. Actually, this is not something that has a really good metric to it. But long story short, the picture we're painting is this. It doesn't fit with the likelihood ratio test. The model doesn't fit with the CFI. It doesn't fit with the TLI. It doesn't fit with the RMSEA. And the standardized root mean squared residual, doesn't really do great there. I wouldn't say this does a good job fitting our data. So I would not even look at the results, because if we did, we may have some biased standard errors. We may have some biased fit main effects. We don't want that to happen. So what we have to do is now modify our model, right? We want this model to fit. This is where the line between generalizability and theory sort of gets blurred. We need model fit to look at the model parameters, but any model modification that we do, particularly those modifications based on p-values, may not generalize as well going forward. So it's a big caution. It's a dilemma that we have to solve. It's not an easy one to solve. What I would like to do today is show you how to do this with model modification. There are certain statistical ways that we can try to modify our model to see where model misfit is happening. This is useful, but remember, it sort of saps generalization. There are more advanced approaches that you could take if you get deeper into the topic. But let's look into this with a couple different areas. First, let's look at the residual covariance matrix. Now, remember, model fit is guided by how well our model's implied covariance appears to look like the saturated covariance matrix. In our case, what we can do is take the difference from what our model says and our saturated model in terms of covariances, literally subtract the two matrices, and then normalize it. So basically adjust those so that the differences are on standard units. These units look like z-scores, right? So here, when we do that, we'll see that there's two very large kind of z-score covariances, differences. Now, I'm using that term lightly, just to sort of give you an impression of what I'm talking about. So, for instance, we know that there's a big covariance, residual covariance between usefulness and math self-concept. And there's also another big negative covariance between gender and college credit hours right here. Those are two areas where we have to look to modify our model. The normalized residuals, to me, function as a target matrix. Hey, where are we misfitting? Where is the model not working well? The previous slide told us overall, globally, it's not fitting. This is telling us where specifically it's not fitting. There's another set of indices we could use as well. Now, this right here tells us where the problem lies. The next set are something called modification indices. In different fields, these may be called score tests or Lagrangian multiplier tests. These are indices that suggest what the change in likelihood would be if you were to add a parameter to the model itself. So I used the mod indices function, and I was able to obtain three different indices. I'm going to target this usefulness versus math self-concept to try to remedy my model fit. I want a model parameter that sort of makes the model fit for this square right here much better. So there are three options that have usefulness and math self-concept in them. The first is a residual covariance between usefulness and math self-concept. This is a parameter that says they're related, but I'm not actually describing why. One is not causing the other. The next parameter here is usefulness. Now there's tilde math self-concept. That basically says we're going to predict usefulness with math self-concept. And the last one is the opposite. We're going to predict math self-concept with usefulness. Now, model identification, that local model identification means we have to pick one of these three. And the one that we pick is one that we have to sort of fit into what our theory would be about, would fit best into our theory about this entire path model, this process of what's describing performance and perceived usefulness. Now, before I get into that decision, let's talk a little bit about the values. The MI column represents what the score tests suggest would be the likelihood. Like if we were to add this parameter and look at the likelihood ratio test between the model with this parameter and the model without. So our model without is our current model. We would expect the likelihood ratio test to be 41 with 1 degree of freedom. Right? Remember, likelihood ratio tests, they follow a chi-square distribution. A chi-square distribution's critical value for 0.05 alpha level, type 1 error rate level, is 3.86. This being much larger than 3.86 suggests this is a very strong effect, very strong, a very small p-value for it. So this tells us that, yes, adding this parameter is likely to make a significant difference in model fit. The next column talks about what the parameter would be if we put it into the model, if we actually estimate it. This is an estimate of what that parameter would be if we estimated it in the model itself. It's almost like we were running a model and comparing it. That estimate turns out to be 70.912. That is the size of the covariance. And you can see this would be regression slopes. These other columns that you see here are standardized versions. We'll just leave those off for right now. So the question then becomes, which one of these should we add to our model? Well, think of it this way. Which one, to me, since I'm not the author of the study and I'm not an analyst that understands this process, I'm not a math educator in this sense, my thought would be, let's pick the one that does the least amount of harm to what we're saying overall. And to me, that's the residual covariance. It basically says, yeah, there is some type of relationship between these two variables that I'm not going to easily explain, but I need to account for in the model itself. So I'm not making any causal claims. I'm not saying that one variable is causing another. What I'm saying is that they're related, and the model doesn't fully explain that relationship. So therefore, I need a parameter there that provides that relationship. Like, we don't shut it down to zero. We let it be there, but it doesn't do so in a way that makes a strong conjecture about the process itself. Now that's opposite to the other two. When you add a direct effect, you're making kind of a causal claim. You're saying, oh, math self-concept causes someone to perceive usefulness. The higher the math self-concept makes them think math is more useful. Or you're saying the flip. The higher they believe math is useful, the higher math self-concept will be. So both of those is a much stronger claim to me than the residual covariance. So we're going to move forward with the residual covariance. Right? Now, the areas in dashed lines here, this is where our parameter would go. There was another parameter here between gender and college math experience, right? So both of these are where those parameters are. Now, I will again, once to note, I can't add more than one of these because they all do the same spot. And if I add more than one, I violate identification conditions. I have a non-recursive path model. So we sort of have to think where that happens to be. So I just described the slide, but I'll just describe it one more time for completeness sake. The modification indices showed three very large values: the direct effects of MSC predicting math self-concept from usefulness, a direct effect predicting usefulness from math self-concept, and a residual variance between usefulness and math self-concept. I will note that the modification index value is -2 times the change in log likelihood. If you were to add the model add that parameter to a model and do a likelihood ratio test. Also, the EPC column is the expected parameter value of the model, of the parameter when it enters the model. So you can think of the modification index as a 1 degree of freedom chi-square test. And 3.84 is our type 1 error rate at 0.05, right there, critical value. So because all three happen for the same variable, we can only choose one. This is where theory should help. But because we're not, at least I'm not a person who's deep into this theory, I'm going to pick the residual covariance. Again, the reason for that is the covariance is unexplained by the model, but it does not make any more inferential claims about anything other than, hey, the model doesn't fully explain why these two things covary. Well, we wouldn't expect it to necessarily. So what that looks like is this. I'm adding a dashed double-headed arrow between math self-concept and perceived usefulness. So I did that. And now here are our model fit. So we have to start over with our path model decision tree, our workflow. The model is now identified, right? We have 20 parameters now. We had 19 before. We added one. It's still less than 28 covariances. You can look here and see now this double-headed arrow here. You're like, wait a minute, is it now non-recursive? Because if I follow this arrow, just remember the recursive rules are based on the direct effects. So still recursive, still estimable. If we go and look at the key sections of the model fit, now we see things look a little bit better. The likelihood ratio test gives us a p-value of 0.072, now 8 degrees of freedom, not 9. If you're using a type 1 error rate of 0.05, that's good. That means we fit as well as the saturated model. You'll also look at the RMSE8 RMSEA is 0.048. That's also good, right? And the probability is less than 0.05. That's 0.48. It's still pretty good though. Our CFI and TLI are above 0.95. That's good. And standardized root mean squared residual also went down. So now we can conclude that the model adequately approximates the covariance matrix, meaning we can now inspect our model parameters. We can get to the reason we're doing this in the first place. Hooray. So here are our model parameters. Okay, how do we interpret these? Well, we interpret these the same way you interpret regression parameters. There's just a whole lot more of them. Right? In the output, we see regressions, and they separate it by dependent variable. So performance was predicted by 3 different variables. And what you end up seeing here is that math self-concept and math self-efficacy are both significant, whereas high school credit hours was not significant. We can see each of that. So again, getting into the interpretation, we could say, okay, for every 1 unit increase in high school experience, performance goes up by 0.15. That is how we would interpret that. Same thing like a regression slope. The intercepts also, we interpret those in a similar way we do in regression as well too. Here we say, okay, the intercept of performance, that is the expected value of performance for a person who has 0 high school math experience, 0 math self-concept, and 0 math self-efficacy. So if you don't know yourself to be a mathematician, you don't feel very strong at your math skills, and you took no math in high school, you'd get unlikely 1 out of those 18 problems correct. That's how this is interpreted. And we can see this throughout. Now we'll note the intercept for gender. This is actually the proportion of people who are in our sample male. That is a mean. It's not explained. It's not a predicted value itself. And you'll see we have a residual covariance here. That was our parameter that we added. And our residual variances, these are the variances for each of the endogenous variables and then the variance of gender. Now let's get into standardized parameter estimates, because you might say, oh, look at this. Some of these parameters are quite large. Like for instance, on math self-efficacy, there's a large impact, or a similarly large impact of high school experience and gender. But yes, however, the problem is each of these predictors has a scale, right? This slope is interpreted as units of math self-efficacy per unit of high school math experience. And remember, high school math experience has a different scale than gender itself. It's on a different metric. Gender goes from 0 to 1. High school math is the number of years of high school math, probably somewhere between 0 and 4. And so if we standardize this, we look at the regression slope. Now what we end up saying, look at the std.all column. std.lv is used in latent variable models. We'll talk about that today. So just look at the std.all column. We'd say, oh, for every 1 standard deviation increase in high school math, we would expect math self-efficacy to increase by 0.45 standard deviations. Whereas for every 1 standard deviation increase in gender, we would expect high school math or math self-efficacy to go up by 0.166 standard deviations. Now, what is the standard deviation of gender? That doesn't make any sense. But the same thing is true for each of these other variables as well, too, as we go forward. Similarly, we could look at this in a little bit more precisely in the performance regression. We have high school math experience and math self-efficacy both having a similarly sized regression slope. But when we standardize them, you see that there's a big difference between each of these. So standardized regression slopes sort of allow us to compare on a comparable metric as to which slopes are more large in a statistical sense, sort of controlling for the differences in scale on the predictors themselves. Well, let's just keep moving on. I'll skip that for now. So what we can interpret, now we can interpret our model. This is just me going through each of those effects, talking about which one is significant. We can say that high school experience is a significant predictor of college experience. So more high school experience means more college experience. We can say that high school experience, college experience, and gender are significant predictors of math self-efficacy. We saw that previously as well, right here. These are all significant. So that means more high school and more college experience means higher math self-efficacy, and that men have a higher math self-efficacy than women. We also have that high school experience, college experience, and math self-efficacy are significant predictors of math self-concept, meaning more high school and college experience and higher math self-efficacy mean higher math self-concept. And you'll note the higher terms here come from the signs of each of these variables, right? If they were negative, we'd say more of one means less of the other. And finally, we'll get to the other variables here. The higher math self-efficacy means significantly higher perceived usefulness. Higher math self-efficacy and math self-concept result in higher math performance scores. So high school experience was not significantly related to performance, though. And finally, math self-concept and perceived usefulness have a significant residual covariance. That means that the model didn't fully describe why they covariate together, but we needed to account for that, whatever was remaining, to make our model fit better. Now, we could also get the R squared for each variable. This tells us how much variance we're accounting for in each. And remember, performance and usefulness were sort of endogenous variables that were at the right-hand side of the path model. These were what we were trying to predict. We do a pretty good job predicting performance, R squared of 0.573, but predicting why someone would perceive mathematics to be useful is 0.044. So not as good about that. So there we have it. Now, as we move forward, we can see that we just described how our path model fit for every direct effect. But if you look at our path model, we'll go back to those slides, there's quite a few indirect effects here. For instance, what is the effect of high school math? There's an indirect effect of high school math experience on math performance, and that it goes from high school math experience to math self-concept to math performance. So basically, as if we think as high school math experience goes up, we say that math self-concept goes up. But as math self-concept goes up, performance goes up. So you would actually see, okay, hey, yes, for every 1 unit increase in high school math, performance goes up. That's a direct effect. But just remember that 1 unit increase in high school math triggers a certain unit increase in math self-concept, which that increase also brings out performance. That's an indirect effect. So we have to go in and look at that. We have to actually describe that a little bit better. So let's get into indirect effects or indirect path. So for instance, going back to that example, because high school experience predicted college experience and college experience predicted math self-efficacy, there's an indirect pathway between high school and experience and math self-efficacy. An indirect path represents the effect of one variable on another as mediated by one or more variables. So this is where mediation comes into play. The indirect path here suggests that the relationship between high school experience and math self-efficacy is mediated by college experience. More formally, the mediational relationship is hypothesized in the path model. A formal test of hypothesis is needed to establish college experience as a mediator of high school experience and math self-efficacy. I'm drilling in on that one because that's an easier one to look at. There are a number of other indirect paths in the model itself, some of which may or may not be interested to your research question. But let's just take a look at that 3-variable relationship here. We've got a direct effect of high school math experience on math self-efficacy, meaning for every 1 unit increase in high school math experience, math self-efficacy goes up 4.138 units. Okay, great. But remember, for every 1 unit increase in high school math experience, college math experience goes up by 0.66 units. And for every 1 unit increase in college math experience, math self-efficacy goes up by 0.393. That's the problem, right? We have 4 units increase directly. How many units increase indirectly? So it turns out we can calculate the indirect effect by taking the product of the two slopes. Remember it this way, right? This slope multiplies that slope, gives us an indirect effect. And why we think about that is this. Again, remember, high school math experience, for every 1 unit increase in it, college math experience goes up by 0.662. Now, we know that this 0.393 is the change of the increase in math self-efficacy for every 1 unit increase of college math. But we don't need 1 unit. We actually need 0.662 units. So that's why 0.662 multiplies this effect. So that product gives us an indirect effect of 0.260. So how do we interpret that? Basically, we say for every 1 unit increase in high school math experience, math self-efficacy goes up by 0.260 indirectly. So it goes up by 0.4138 directly and 0.260 indirectly. Right? Again, the indirect effect is the amount of increase in the outcome variable that comes indirectly by a 1 unit increase in the initiating variable. Right? So in this case, math self-efficacy is the increased variable, and then the initiating variable is high school math. Right? As high school math experience increases by 1 unit, college credit hours increases by 0.662. And then well, you can see the rest of it. We've just been over that. So, and then finally, we could take the indirect effect and the direct effect and describe something called the total effect. The total effect represents the total increase in the outcome variable for a 1 unit increase in the initiating variable. So in this case, it's the sum of the direct and indirect effects. So we have our path. Basically, we're saying for every 1 unit increase in high school math, math self-efficacy goes up by 4.1 units directly, and by this product indirectly. And if we do the math on that, it becomes 4.398. So we interpret the total effect similarly to how we interpret a regression slope. We'd say for every 1 unit increase in high school math experience, math self-efficacy goes up by 4.398 units in total. That means total between direct and indirect effects. So to me, this is an excellent way of describing effects of models. And this is the value of path analysis, in that you get a much more rich picture of how not only variables directly impact, one variable directly impacts another, but how it may indirectly impact another. So therefore, now we have a multivariate effect, thereby putting it into a multivariate class. Now we can do a hypothesis test for this as well too. And in Lavon, it takes a little bit of syntax, but it makes it work, right? So we just quantified using, products, making a multiplication, what an indirect effect is. And then we added that to the direct effect to make a total effect. We didn't quantify whether each of these is statistically significant. Now, determining how we make this significance test is difficult. It's not as straightforward as the GLHT function in linear combinations, because we're making a product of parameters. That product of parameters doesn't follow a normal distribution. So what Lavon will do is take a bootstrap resample of our data to try to get a p-value for each of these. So how we have to do this, we have to label the parameters of interest. In Lavon, labeling is where we take a character string and we put an asterisk. It looks like this is another variable, but Lavon will look at it, not finding it in our data, and say, wait a minute, that's a label, right? So we have a label here, it's a placeholder. And because it shows up on the line where we're predicting math self-efficacy, that placeholder takes the place of the slope, the direct effect of high school experience on math self-efficacy. We have another placeholder here for college math on math self-efficacy. And we go down to college itself, we have the placeholder for the direct effect of college math, of high school math on college math. Those are the three terms we need. Now with that, in Lavon, we can define a new parameter or variable that will estimate and give us a hypothesis for by the equal or the colon equal syntax. So we give it a name. This is the indirect effect of high school math on math self-efficacy. That is the product of those two direct effects, the slope of high school on college and the slope of college on math self-efficacy. And then the total effect, which is I'm defining as TOT HSL MSE, that is the original slope, the direct effect of high school on math self-efficacy plus the indirect effect itself. When we do this, we actually get an output in Lavon where we can see not only these parameters, we can get the p-value for each, and we can see the standardized coefficients. And this is how we would interpret those. Here, again, we see that 2.260. We see that is at a 0.05. Its p-value is 0.019. So if you're using a type 1 error rate of 0.05 or thereabouts, that would be significant. And you can see its indirect or sort of standardized effect as well. How we'd interpret these would be the same as we interpret each of the other terms. The indirect effect is how much math self-efficacy increases indirectly for every 1 unit increase in high school math, math self-efficacy indirectly increases by 0.26 units. The standardized version of that would be in standard deviations. For every 1 standard deviation of high school math we increase, the math self-efficacy indirectly increases by 0.29 standard deviations, 0.029, excuse me. Not a big effect. And then finally, the total effect, so for every 1 unit increase in high school math, math self-efficacy in total goes up 4.398 units. That standardized effect, again, for every 1 standard deviation in high school math, math self-efficacy in total goes up 0.488 standard deviations. And here, because this indirect effect is significant, we would say that college credit hours mediates the relationship between high school math and math self-efficacy. If this term was not significant, what we would see is two things. This parameter would be closer to 0, so we'd say there's really no relationship. And if this parameter is 0, because it's added to the direct effect to produce the total, we would expect this total effect to be no different than our direct effect. So that's mediation in a path model context. Now, there are a few other conditions to think about, modeling considerations, I guess, to think about in path analysis. I'll go through those pretty quickly here. This is meant to be an introduction to a topic that's quite frankly very dense. A lot of material written about it dates back over 100 years. The reality is, if you're going to do a path analysis, I would encourage you to go study this a little bit more. It's much more complex than what I'm describing in this lecture. This is much more an introduction. Our path analysis assumed all variables to be continuous and multivariate normal and predicted or measured with perfect reliability. In reality, neither of these are true. Like most of our endogenous variables are scales of some sort, so those reliabilities are not one, violating this. And the gender variable was binary, which violates multivariate normal. Now, structural equation models, which are path models with latent variables, will help with the variables measured with measurement error. What we actually end up doing is building a measurement model to separate measurement error and predict the latent variable directly. But we also can define path models with differing distributional assumptions. Sometimes this is easy in software. Lavon and M+ will do this in what we call limited information estimation. Not exactly maximum likelihood, but works pretty well. This also gets us into Bayesian estimation, or we could build our own estimator itself. I don't recommend the latter, but it's possible and people have before. Now, another thing that we want to talk about is causality. You may hear in causal inference what the path analysis, this graph is. Sometimes it's called a directed acyclic graph, right? A recursive path model is a directive acyclic graph. That carries very special meaning. The causal analysis literature sort of grows from it. This is not a causal, basically trying to come up with causal claims about what we're doing. The hard part with that is causality can rarely, if ever, be inferred on the basis of observational data. This is not an experiment we ran. And even if you have an experiment, it may be the case that causality may not be able to be inferred either, right? So just because we have a very fancy model, path analyses and variables and so forth, doesn't mean we're getting around the issue that this is not necessarily a causal process. We're giving our best information about it, but really to make causal claims, we need a much more experimental design, right? Model fit is a nice index. I will tell you that we can falsify causality, perhaps, right? If your model doesn't fit, causality is not likely happening, right? However, if the model does fit, causality could be one reason for it. And beyond that, there are a couple other features of path analysis that I didn't talk about that are difficult, in that if you take one directed path and switch its direction, so long as the model is recursive, the model fits just as well. So what we're doing is really describing covariance through directed effects. And that is not at all causality. It's just disentangling something that could be observational. So I used the word causal before, but do not use that word as you go forward. It takes a lot more evidence to suggest this is a causal claim. Now, we could try to assume it. We could make an assumption about it. We can go further study it. But the direct result that we have here is not causal. So that's it for this lecture. It's an introduction. We talked a little bit about model estimation, specification and identification. We did a little bit of model fit. We did model modification, and we did our final parameter interpretation. And as you can tell, there's a whole lot to the analysis. What is important to remember is that the overarching principle of multivariate analysis, that covariance between variables is important, or more broadly, the joint distribution of variables is important. Path models imply a very specific covariance structure, and the validity of the results hinge upon accurately finding approximation to that saturated model covariance matrix. So that's it for me. Thank you for listening.